everybody. Hope everybody's doing well out there today. All right, we're starting a new unit. We're starting a new set of things to really interesting stuff to learn about. But before we get to that, I want to talk to you about next week. I would like to go ahead and try to set up a Zoom classroom for next week. I'm missing seeing your faces, and it wouldn't be for the lecture, okay? So I'm going to go ahead and record the lecture like I'm doing this one, and I'll send that to you probably on Monday. But on Tuesday, if at class time, which is 1 o'clock, we could go ahead and get together with a Zoom class. And if you have any questions, or if we can try to settle some of these problems like with the quizzes and things like this, perhaps we can get that taken care of next week. And then I can see your faces and all that. If you are unable to make it to it at class time, like say a sibling is using the computer or something like that, I'll record it, I guess. We can figure that out too. All right, so we are going to start now on Module 14. So that means I will be sending along the quiz for 13. Now, I think this class was the one I was able to get the quiz 12 into Google Classroom. Isn't that correct? And some of you got that back to me. I haven't got it from everybody yet. I have had students send it back by taking a picture of it with that thing called Genius Scan. Turns it into a PDF, which is really nice. So that works really well. So if you get the opportunity to download that free program, Genius Scan, that works really well. Okay, so here we go on learning about sound. Yes, here we go. All right. So energy can travel in waves, and sound is a form of energy wave. So we're going to look specifically at how we believe it travels today. So here's your first blank you're filling in. Sound travels in waves. Therefore, it's energy, right? And there are two basic forms of waves that we know of. We have a transverse wave, and the definition of that is the direction is perpendicular to the oscillation. All right, we'll get into those words and what they mean. You know what perpendicular means, right? So that 90-degree angle. Oscillation is going to be the movement of the sound, the waves moving, all right? So a transverse wave is one of them, and the other one is called a longitudinal wave, where the direction is parallel to the oscillation. So we will see how both of these work. Remember, if you need more time writing down these definitions, you can pause the video. So the top shows the longitudinal wave and how it works. We can see that it's going back and forth, sort of. Remember, sometimes they can oscillate. So if you've ever had an oscillating fan, it goes back and forward, back and forward. The energy is going this way, and then we'll see in a minute how that what that looks like. Then we have the transverse wave, probably the more familiar of these. You're going to draw this in just a minute. Don't use this picture to draw it. I have a better one for you. All right, but that kind of is like the waves in the ocean, right? So let's watch a little video that explains that real quick.
Ocean waves are a good example of transverse waves. The medium in which the waves travel is the water of the ocean. The wave oscillates this medium vertically. In other words, the water rises and falls as a result of the wave. However, the wave's propagation is horizontal. In other words, the wave approaches the shore. So its propagation is perpendicular to its oscillation. That makes it a transverse wave.
Okay, did that make sense to you? Maybe not. Let's look at it this way. This is what I'd like you to draw. Okay, so I believe you have a box in your book there, and you can draw this in here. Not only draw it, remember whenever I ask you to draw something, I'm assuming that you understand that means also that you will be labeling it, okay? So draw it and label it. I do know that there is one problem here. So notice this line going through the middle right here, okay? This is a little misleading right here. The amplitude goes from this line to this to here, okay? From here to here. It also goes from here to here. But it doesn't go from all the way at the bottom to all the way at the top. So it's a little misleading. It does go here from the middle up and from the middle down. So I'd have you just don't draw this bottom part right here, okay? Just draw this top line going up here like this. You can put it in the middle of a crest if you like, if it makes you feel better right there. So we have our crest is the top of it. Our trough is the bottom of it. from one crest to another crest is called the wavelength, okay? And then from the node or whatever, from this line here, the amplitude is how high does it go up to its crest or trough, okay? So because they're about the same, right? The crest and the trough should be even, and that's why we put that middle line right in there. So that's the direction of medium oscillation, and the direction of energy is this way, and the oscillation is up and down, up and down, up and down, up and down. Okay, does that make sense to you? All right, remember you can pause this to draw this. Now, frequency and wavelength are related, and we have a mathematical formula. Hooray, we have some math we're going to be doing again. You got to love that. All right, so you need to either write that down or put a star by it. There's either a box for you to write it down or it's already written for you, but put a star by it. And it says here that frequency equals speed over wavelength. All right, so we're going to be seeing that frequency, what it is, that's how frequent it is coming toward me. All right, and I'm going to put a little star. That little star is wiggling there to say, remember this one? We're going to need it for the quiz in 2 weeks, right? Okay. This is our frequency and the wavelength inversely proportional, and the answer is it is yes, it's true. They are inversely proportional. But what exactly does that mean? Well, first of all, what it means is that our math problem is a division problem, right? Because that's inverse right there. But secondly, what it means is, this next slide will show it really nicely. When the wavelength goes down, the frequency goes up. When the wavelength goes up, the frequency goes down. All right, so as one increases, the other decreases, and vice versa. So that's what that inverse proportionality means right there. All right, so we'll see how that bears out in some math problems here. Okay, so here's our first one. This is example 14.1. What is the frequency of a wave that travels at a speed of 3 meters per second and has a wavelength of 0.5 meters? Well, this is pretty straightforward, isn't it? It's asking us for the F, and we've written this down somewhere so you can be looking at that formula right there. So there it is, right? So we have our 3 meters per second. That is given to us. And then our 0.5 meters. Notice how meters will cancel out, and we're going to end up with 1 over second. So our answer is going to be 6 1 over second. And it turns out that 1 over second like that is the same thing as a unit called Hertz. HZ stands for Hertz. And Hertz is named after a man, Mr. Hertz, who did a lot of work in this, and therefore he gets that named after him. All right, so that wasn't a very difficult math problem. Easy breezy. You don't even need your calculator for that, but you may use a calculator for it. So when we're looking at longitudinal waves, this becomes important because it turns out that sound travels not in transverse waves, but in longitudinal waves. All right, the direction of the wave moves parallel to the direction of the oscillation. So down below here, you can see sort of a spring type of a thing. If we were together, we would be using a slinky and moving the slinky. I'll show you a video of it here in just a minute. And it shows you the way that it's moving. Now, it's kind of difficult to show it when it's static like this, when it's not moving, but we have the to and fro motion, and this is saying of molecules, right? Because the molecules would be the sound. So my voice, for instance, is traveling through the air, and it's oscillating the air. It's causing the air to go to and fro, to and fro, to and fro, and then it's also moving forward toward my microphone, and presumably from the speaker toward you. All right, that's how sound works. And let's watch a little video about it.
Under the right conditions, a slinky can be an excellent example of a longitudinal wave. Notice as the slinky is being shaken back and forth, it clumps together and pulls apart. Those are the oscillations of the wave. The wave's also traveling in the same direction, however. So in this case, the wave's propagation is parallel to the oscillation of the medium, and that makes it a longitudinal wave.
All right, did you see those, this will show a little bit, where they kind of clumped up in the middle right there? You can see that when he was wiggling that, that slinky back and forth. These right here where they're clumping up are called compressions. All right, so where a longitudinal wave bunches up, that's the compression, and where it spreads out, that's called the rarefaction. All right, so that's what we would call those things. And we're seeing that is how sound, it kind of pushes through that way. By bunching up, spreading out, bunching up, spreading out. This is showing you the pulse right here. So the longitudinal pulse, you see how it starts? It moves through. Now notice the springs themselves really aren't moving very much. Just the energy is moving through them. All right, the energy is moving through it. And that's how sound moves to you. The energy moves through the medium of air to get to you. All right. This is a fun little experiment right here. I've tried it before and never been able to work it out. This is an old speaker. And then what they've put into it is a mixture of cornstarch. You know, we've used this, right? The cornstarch and water with a little Bluetooth coloring. And you can see this crazy way it acts as the sound moves it. This shows you that there's a lot of movement in sound. The waves are moving. This would be a great project to try. You might wonder what kind of speaker that is. I think it's like a bass speaker. And since it's not hooked up to the right thing, it doesn't make any real sound. You'd have to look up how to get the sound to go through it. I've never been able to figure it out. Look, that's crazy. It's just jumping up out of there. Okay, so a lot of fun right there. So now we'll look at the sound in the ear. So if we have our transverse wave traveling along, you can see our compressions and our rarefactions there. And then on this end, it's hitting a membrane over here. This blue thing is a membrane. And we're going to think of that membrane as like part of our ear. Okay, because right now you're listening to my voice through a speaker, through an earphone or something like this. And what it's doing is those waves are coming to you on this in this pattern, and they're vibrating. So the sound waves are vibrating, and then it's going to vibrate our part of the ear. So, which is pretty cool. Now, you know, you can, if you put your hand to your voice box, to your throat while you're talking, you can feel those vibrations of the sound going through it. You know, if you're not talking, that vibration isn't there, but if you are, it is. Because the air is being pushed out through our vocal cords, and our vocal cords are vibrating. And now it's going to come in through our ear. So our ear, on the outside of our ear, the pinna right here, or the ear leather, however you want to call that, is shaped a little bit like a funnel, and that's to bring sound into the ear canal. Okay, so we have the sound wave. Here's the wave coming through. Hits our outer ear, comes in through the ear canal, and right here, it hits the eardrum, okay, the eardrum. And that's what's the blue thing in the previous slide, is it starts to vibrate. And it is connected to 3 bones right here, the smallest bones in the body, the incus malleus and the stapes. And then those connect up to this right here. It's called the semicircular canals and the vestibule. This area here is the sound is vibrating through air. In the middle ear, the middle ear, it is still vibrating through air. So this is filled with air. All right, you know that when you go up a mountain and your ears start to pop, that's because this little tube right here, called the eustachian tube, will flatten out. And when you chew gum or something, it'll help open that back up, getting air reestablished back in here. But when it hits the vestibule right in here, these vibrations are at the end of this little stapes, also called the stirrup, right? And it hits this and starts to vibrate, and there's fluid inside this part. All right, so the fluid is in this vestibule and the semicircular canals right here. Now, all of this right here has nothing to do with hearing. So the sound that's here, what this has to do with is balance. Okay, so that's a different sense. So we're going to skip that for now and come over here to the cochlea. Cochlea means snail. It looks a little like a snail, doesn't it? And this is also filled with fluid. So these waves are coming in through here, and they're hitting another similar to the eardrum right over here. It's actually called the oval window. And when it hits there, it vibrates through the liquid inside the cochlea. It actually goes all the way around and then turns around and comes back. And there's little hairs inside there, and those little hairs will pick up those frequencies of the sound coming to you. And there'll be several things that will happen. So if they're low frequencies, they'll be picked up in one part of the cochlea. If they're high frequency waves, they'll be picked up in a different part of the cochlea. And then our brain will interpret those things. And furthermore, your brain will have things like memory. You can remember the sound. For instance, if you hear a harmonica, you can say, oh, that's a harmonica, because you remember it. Right now, you're hearing my voice, and you know it's me because you recognize my voice, hopefully. Hopefully you're not sick of it by now. So here's a nice little animation of what's going on. So the air traveling, the sound traveling through air through the ear canal, hits the drum. Notice how it's causing the vibration. It's vibrating those 3 bones right here, and then it's going to hit the inner ear right here. So there's the cochlea that we're talking about. Now the next slide is going to show another animation like this, but into the cochlea, but it's a little annoying, so I apologize for it. All right, so there's those 3 bones. They're really, really moving fast. So notice it's going to go into the cochlea, all the way around. It's simplified a little bit, and then turn around and come back this way. All along the way, it is vibrating little hairs, and those little hairs will interpret the sound that we get. Okay. Now, I've been telling you how the sound is traveling through the air. So my next question for you is, does it have to travel through the air? Does it need air? Can it travel in a vacuum? Well, the short answer is no, it cannot. And we'll show it here in just a minute. But we do have a speed of sound that, as long as it has something to travel through, we can use this equation right here. So we have V equals, you're going to have to write this down or put a star by it. It might be in your book already, or else it has a little box to put it in there. So V equal 331.5 plus 0.6 times big T meters per second. So what do you think the big T stands for? It actually stands for temperature. Isn't that interesting that temperature makes a difference to how fast or slow something will travel, sound will travel in the air or anything else? We're going to watch a little video here that's going to show you about sound in a vacuum. All the air out of that jar. Listen to the sound. You can see on the scope, the oscilloscope down at below, that the sound is still going in. But you can't hear it very well. You hear it now? Now listen. Letting air out slowly so it doesn't damage the speaker. Okay, so you saw that when it was in the jar right there, the sound got very, very dim. And you might wonder, well, why didn't the sound stop altogether? Why did we hear some of it? And well, the reason is that nature abhors a vacuum, right? So a vacuum, trying to achieve total vacuum here on the planet is very difficult. It's a difficult thing to do. Remember we watched that really great video about the silo, and they got all the air out of the silo and dropped the feathers and the bowling ball at the same time? So that, that's a pretty fancy deal, and it took them hours and hours to get the air out. But they never did get all of the air out of there, because we really can't do that, just because it's something that we're limited here on the Earth to do that. We're going to try something similar like that in our little lab here in just a few minutes. All right, so the speed of sound problems, we're going to do a couple of these. Remember our speed of sound. V equals 331.5 plus 0.6 times temperature meters per second. Remember that distance is speed time time, so we'll need to remember that. And remember that the air temperature makes a difference. Sound travels faster in warm air. Does that make sense? Because think about it. If the air is warmer, that means that the molecules are traveling faster, right? And if it's cooler, the molecules are traveling slower. We remember that when we talk about like cold water versus warm water, didn't we put food coloring and see the difference of how those moved in there? So the same thing is going on with air. So let's try a practice problem. Here we go. 14.2. If the temperature is 68 degrees Fahrenheit or 20 degrees C, what is the speed of sound? So we want to ask that question. What's the speed of sound at 68 degrees? All right, so we're going to figure this out. Here is our formula. We're going to go ahead and put the 20C right in there. That's the Celsius one right in there. And we're just going to do that math. All right, we're going to multiply first, then add. So we're going to end up with 331.5 plus 12. And there we go, 343.5 meters per second. So how fast is sound traveling at 68 degrees? It's traveling at 343.5 meters per second. All right, so that's not too bad. We're going to need to use this formula next week when we do our little lab. We're going to actually try to collect some data and get the temperature of the room and pick up a frequency and try to figure out how fast the speed of sound is. I believe that's what we're going to do, yeah, in our lab next week. Okay, next problem, example 14.3. And here we go. A physicist is watching a thunderstorm. Awesome. She sees a flash of lightning and then hears a thunderclap 2 seconds later. If the air temperature is a cool 15 degrees C, how far away from the physicist was the lightning formed? This is always a lot of fun, right? In a lightning storm, you hear it, you see it, and you start to count, right? Count the seconds, and you can figure out how far away it is. And, you know, furthermore, the next one that comes, if it's closer together, then you know that it's moving towards you, right? The storm is moving towards you. All right, let's do our math. Here we go. There is our formula. There's our 15. Where did we get that? We got it right here. Right here. It was given to us, 15 degrees C. And we're going to put it right in here. This we already knew, right? Because that is the given formula right there. We were just adding in the extra information of temperature. We did our multiplication first, so we have 331.5 plus 9, and our answer is 340.5 meters per second. All right, so the speed, however, is the distance traveled divided by the time traveled. So let's say that. Distance traveled equals speed times time. So we're having to do all this, aren't we? So the distance then is 240.5 meters per second. That's our speed. Times our time, which was given to us right up here, 2 seconds, which brings us up to 681 meters. So now we know it was 681 meters away, right? Okay, so you might end up with a problem kind of like that in your quiz. So the speed of sound in other substances. Do you remember when we were learning about the way that the mantle is formed and it's sort of that liquid rock? In fact, we made some of that cornstarch with the water. Remember the mess we made? Yeah. So also that time, do you remember that we did a little test we had a stethoscope and a tub of water and the spoons, and we clanked the spoons? And remember how the sound traveled through the water really well? Even better than through the air. And so just keep that in mind here as we ask these questions. So does sound travel faster in a solid or a liquid? We're going to see a video here in just a minute that's going to show this. It's going to be the solid, because the solid has all those molecules packed so closely together that the sound can oscillate through it, because it has a lot of stuff to oscillate through. Does sound travel faster in a gas or a liquid? This one's easy. What's the answer to this one? A liquid. And does sound travel faster in a solid or a gas? Also an easy one. That's going to be solid right there. Okay, because right now sound is traveling through a gas. It's traveling through the air to you. And we've discovered that now, while our ears are made perfectly to receive sound that travels through a gas, through the air, that it really travels much better through liquids and solids. We discussed how if you were in a fallen down building and trapped, you, instead of yelling out help, you want to start banging on something. Use something metal to bang on a metal pipe or something, and someone will be able to find you, and you'll just get worn out if you try screaming. This is the picture I showed you back then, and I'm showing it to you again right here. So if we all strike the end of this tube at the same time through a solid, it gets there the quickest. The waves are reaching the end the quickest. Then comes liquid and the gas. It's slower. It's slower to get there through the gas. All right. Let's watch a little video. This is going to show about sound moving and that kind of thing.
If you don't believe that air vibrates, take a look at this. Sound waves can travel through solid things like wood as well. The particles in a solid are packed together far more tightly than air particles. What difference do you think this makes to the sounds you hear? Listening with a stethoscope can hurt. Does sound travel faster in the ground or through the air? And is the speed of sound ever as fast as the speed of light? To find out, you need to make a sound that can travel a long distance. 5 tons of plastic explosive should do the trick. How would you detect sound waves in the ground? Samantha's going to watch for the explosion, but she's wearing headphones so she can't hear it. Fung is going to listen for it, so he's wearing a blindfold. And Elizabeth's going to detect sound waves in the ground.
Ready?
Ready?
Ready.
So, who's going to be the first, second and third to detect the explosion? They were waiting to see the light, hear the sound, or feel the sound. Samantha was first because the light got to them before the sound. Elizabeth was next when she felt the sound coming through the ground. And Fung was last, when he heard the sound of the explosion coming through the air. The speed of sound in the air is 350 metres per second. At 5,000 metres per second, sound travels much faster through the ground. But light is much faster than any sound, at 300 million metres per second.
All right. Too bad we couldn't do that experiment in class, huh? That would have been fun to put some explosives in the ground like that. Okay, so what is a sonic boom? That is a sound. We don't hear it as much anymore. When I was growing up, it was a little more common. But it turns out that when an object travels faster than the speed of sound, which is about 775 or 774 miles per hour, that a special kind of a noise takes place, which is called a sonic boom. Mach 1 is traveling just about the speed of sound. That's what it means. Okay, Mach 3 is 3 times the speed of sound. So that's what those words are all about right there. Okay, so if an object is traveling faster than the speed of sound, that is the definition of a sonic boom, and we're going to see why it does that. But in your blank right there, you're going to write that first bullet point right there, that it's going faster than 775 miles per hour. Not many things can travel that fast, right? So it's not like anything can just go faster than 775 miles per hour. I do believe that the land speed record, so a car moving across very flat ground, is right at about 800, I think. Maybe we could look that one up and see if that is the case. But what we do know does break the speed of sound would be an airplane. Okay, so airplanes are going to be sending out. So here's an airplane. It's stopped right here. Its engines are running. So therefore, it's sending out sound in every direction like a ripple in a pond. But when it starts to move, it's producing sound, and it starts to move, and it starts to compress. Remember our compressions and rarefactions? It starts to compress those sound waves right here at the front. If it goes fast enough, 775 miles an hour, they get absolutely compressed right here in front of it. If they're supersonic, greater than that, then the sounds are compressed behind the airplane. So interesting here, the guy who is flying this airplane won't hear his engine noise anymore. It'll all be behind him. That's crazy. Here, what'll happen is that at this point, when those compress, they make a loud sound. This is an airplane that has just broken through the sound barrier. All right, it's almost like going through a wall, right? This is a cloud. It's a very common occurrence, especially if there's some humidity in the sky. But this cloud forms when all those sound waves get compressed, and then we have a condensation of the moisture that's around it right there. Okay, and so he's just broken that. We're going to watch a little video now. This gets a little loud, so guard your ears. Okay, so what happened there, I'm going to go back a second. So what happened there is that as he was flying through, notice they were on a boat over the ocean. And the reason that is the case is because, our government has outlawed these airplanes making sonic booms like this. You think, well, why are they outlawed? Well, it's very loud. When I was a child, I heard some. I lived on an army base. My dad was a pilot. And it would rattle the windows. And it got to the point that in cities that the sonic boom was so loud that it was literally breaking windows and things like this. So the government essentially said, no more of these sonic booms. They're way too damaging. The planes don't need to be going that fast. So the only time that planes go that fast, and we're talking mostly fighter jets and things like this, it doesn't make sense for the big commercial airlines to go that fast. It has to do with the amount of fuel they're using and this kind of thing. And they're also much bigger, so I don't even know if they can, but I suspect they can break the sound barrier. But when they do break the sound barrier these days, they do it over the ocean, so it doesn't bother anybody. And so this particular video showed them over water, right? Now, we're going to watch it again, and I want you to pay close attention. You're going to see this cloud form on the airplane, but you don't hear it. All right, so just like our last video we saw, you see it, so the light gets to our eyes much quicker than the sound gets to our ears. So let's watch it again and pay attention to when you see it and when you hear it. Right there and there. You heard the two booms, right? The two booms, because it did it twice right there. All right. Am I going to the next one? Yeah. Okay. Now, temperature does matter. Sound travels faster when the molecules are moving faster. That makes sense. If the air is cold, the gas molecules are not moving so fast. So the oscillations are slower than in warm air. So warm air is better for faster sound travel. Okay, very good. Now that brings us to lab time. We would have done this in class, of course. And this is, if you remember, my little vacuum set. Remember we had this as a balloon we put in there, and we saw how, we vacuumed the air out and stuff like that. So I recorded this, and then I had trouble getting my little speaker to work, so I was going to re-record it. So there's a couple problems with it, but let's go ahead and watch it. Okay, students, here we go. What I have here is this great little speaker right here, and I got it specifically because of the size. And so notice it'll fit right into our little vacuum. Remember this vacuum kit we used before? We had the balloon in there and stuff. Okay, so I'm going to put some music on, okay? And it's going to play over the speaker, I hope. Okay. A little Mozart going there. Can you still hear it? Now I'm going to suck out the air. Okay. Sounds like it's getting a little louder right there. It's really hard to get a complete vacuum, Okay. Okay, I'm going to bring it up close to the camera here. You can hear it a little bit, right? But now I'm going to undo it. Okay. Okay, so that I wanted to redo that and maybe not have that speaker on quite so loud, and then it would have shown it a little better. All right, the next part of our lab here is using tuning forks. So I have a tuning fork. I'll show you a picture of it over here, how that works. Notice it's got, this is the note that this one, what is a tuning fork for? It's namely to tune, for instance, a piano or something. So you strike the fork, it makes a vibration of a particular note at a particular frequency. All right, so that frequency is right here. It's written down in these numbers right here. Okay, that's going to become important to us next week. All right, so we strike it, and these tines right here of the fork, they start to vibrate, and they produce that note. So someone who is tuning my piano can listen to that note and then play the piano key and then try to bring those in and change the piano strings to match that note. All right, so I'm going to do our little lab right over here. Okay, so this is my set of tuning forks right here. And so if we were together, you would each probably get your own tuning fork and things like that. So what we're going to do is, first of all, we're going to listen to each one of these. And so I'm going to hit them on here. The way they're built like this, you see, is that you hold it right here. So that leaves the fork tines right here to vibrate freely. Okay, and they'll make a sound. If you hold it right here and try to hit it, these won't vibrate, so there'll be no sound coming out of it. Okay, so you're going to take it right here, or I'm going to take it right here. I'm going to strike it on, and I'm going to bring it up close to the phone so you can hear it really well. Okay, hear the different tones. Here we go. And I'm going to actually touch the end of it here. See if that makes a difference. Okay, I would have had you touch it to your ear. You kind of the bones in your ear, and you would hear the way it sounds. The sound travels better through the solid part of your bones. Here comes the next note. Okay. The next one. You're 2 octaves on that one. Once again, 2 octaves. Okay. All right. So you see each one of them has on here a little wavelength right here, and then the note that they are. This one, I don't know if you can tell right here, it says the note is C. Okay, so this is C. Let's see if when I strike this one, can we actually see the vibrations? Can you see it moving? I can. I don't know if it picks it up on the video at all. We'll see. Okay. Also, which would have been a fun little experiment for us, is we can take here and we can see how sound actually moves things. All right, so I'll take this this one here, and I'm going to strike it against the box. It usually gives a better vibration if you strike it against something hard like that. All right, and then I'm going to see if I can try to move that water right there. Oh, did you see that? Pretty cool. So I was able to move that water right out of there. And you see it's because those sound is vibrating. So eventually you students would have water all over the place. All right, very good. Okay, so I don't know why sometimes when I touch the tuning fork to the phone, you could actually hear it coming through the phone, you know, because it was touching the solid parts of the phone. Now, some of them work better than the other. It's probably because I wasn't really paying attention to where I was touching it on there. But those ones that worked really well, you could see how it traveled through that solid part of the phone better than just through the air, right? And so similar to what was happening in that previous video with the little girl who had her teeth on the metal thing, you might have thought that was kind of gross, but really it's because you can feel through there. So oftentimes what I would have you students do is that you take your tuning fork, you strike it, and then you bring up the end of it. So this end right here would be, and you touch it sort of to the little part of your ear that's by your face, you know, so not the part sticking out. And you could put it there and you'd feel it vibrate through the skull, really. And then the brave ones of you, I would have you take it and strike it, and then use your teeth to bite on that very end right there, and you'd be amazed at how that sounds as it travels through the solid part of your teeth. It's crazy. It really gets very, very loud there. All right, so this is it for Module 14A. You're going to go ahead and start, reading through the second half of 14, and so then next week we'll do the second half. We're going to try to work on getting some wavelength frequency stuff going for next week, using sound waves again, using our tuning forks again. All right, that's it, gang, for this. There is an experiment in your book called Extinguishing a Candle with a Sound. We would have maybe tried that. The problem is sometimes when we do it the way the book tells it, it wasn't really the sound so much if it was you pulling back and letting some air pass through it. So I think it's a little faulty right there. But if you can figure out, like in that video where we saw the drum was beating and making that movement right there, if we could find the movement that's a little more pure like that to snuff out a candle, that would be good to go. All right, and that's it. Y'all have a great week. And remember, next week we're going to try to Zoom a class together. And I will be sending out a quiz for you this week pretty soon. Okay, thanks, everybody.